Hello and welcome. This is a work that we present at this year's IEEE Conference on Control Technology and Applications CCTA 2025. And this work is about the robust space-time A-star for human in the loop, MAPD, that stands for multi-agent pickup and delivery. This research addresses a critical challenge in modern warehouse automation, namely how to coordinate robots and human workers safely and efficiently in shared workspaces. Let me start with the background. The warehouse automation industry is experiencing unprecedented growth, driven by several key factors. E-commerce has seen remarkable expansion, yet we are facing a significant labor shortage. Also, customers nowadays are demanding faster delivery times as ever, putting additional pressure on warehouse operations. What's particularly striking is that in a typical workflow of a modern warehouse, order picking alone accounts for 40% of total operational time. So how to automate this order picking using teams of mobile robots is a key to efficiency of warehouse logistics. There are two representative problems studied in the literature. Multi-agent path finding focuses on finding collision-free, deadlock-free path for multiple agents while minimizing total travel time, or the make span. However, it assumes static goal assignments, which is limiting for real-world applications. Multi-agent pickup and delivery is more complex and is an extension of the multi-agent path finding. It combines task allocation with path planning, supports dynamic task assignment throughout the system's lifetime, and requires much more sophisticated coordination. Here the figure shows a typical multi-agent pickup and delivery scenario where multiple agents must navigate a warehouse environment, picking up items from various locations and delivering the items to designated drop-off areas. The colored path represent different agents' trajectories, and you can see how complex the coordination can be even in this relatively simple example. In the literature for multi-agent path finding, we have several established approaches, including conflict-based search, priority inheritance with backtracking, and hierarchical cooperative A-star. For multi-agents pickup and delivery, researchers have extended all these basic approaches. Despite extensive work that has been done, there are key limitations of current approaches when applied to real industrial settings. They typically allocate only a single task per agent, ignoring payload constraints that allow agents to handle multiple items efficiently at the same time. They assume instantaneous pickup and drop-off operations when real-world operations take time. They ignore power and energy limits that are crucial for battery-powered robots. Most critically, and this is what we address in this paper, they assume robot-only environments, thus overlooking human workers. In this example down below, you can see a typical warehouse scenario with arriving picking tasks throughout the day. Current algorithms would treat each task independently, but in reality, we need to consider task grouping, times for pickup and drop-off, energy consumption, and most importantly, human workers who may be performing similar or complementary tasks in the same space. To address these limitations, we have conducted a series of work. In particular, we have proposed algorithms that addressed the first three limitations, and if you're interested in, the references are included, and please check them out. In this work, we aim to address the last and most challenging limitation. Instead of robot-only environment, we are now considering mixed human-robot environments where human workers and robots must cooperate safely and efficiently. Now let me formulate our human-in-the-loop multi-agent pickup and delivery problem. Our setting includes a connected graph environment with N robots and M human workers. We group dynamically arriving tasks and assign a task group to a robot with appropriate payload. Also, robots should have sufficient energy to complete their assigned tasks and return. The key addition in this work is uncertainty. Humans may deviate from their assigned path in both time and space. We are considering a scenario where the humans are also receiving the path planned for them because the environment with robots inside may not be safe. So instead of letting humans decide where to go in the warehouse by themselves, the system will plan safe paths for the humans. And this can be implemented by, say, using tablets and cell phones. The planned paths will be sent from the system to their devices on the hands of the humans. So under these settings, we aim to plan safe paths for both the robots and the human workers to complete all their assigned tasks. Energy constraints of the robots should never be violated, and every pair of robot and human path respects given uncertainty parameters. We'll talk about these in more detail later. In addition, we try to minimize the make span while accepting suboptimality for tractability. The example shows on the left how arriving tasks are grouped, and on the right demonstrates both robot path in blue and human worker path in red and yellow in the shared environment. The key is to consider the temporal and spatial uncertainties of the human movements as shown in the bubbles around the humans. Our solution builds upon conventional space-time A*, but incorporates robustness against the human uncertainty. Conventional space-time A* operates in a 3D search space of x, y, and time t, and treats previously planned agents' paths as obstacles in this 3D. The algorithm computes shortest paths using A*, waits when collisions are detected, and registers paths in a reservation table. This figure shows the classic space-time representation where the time dimension is explicitly modeled, allowing for path planning in this space. However, this approach assumes perfect adherence to planned path, which may not be realistic for human workers who may naturally deviate due to fatigue, distractions, or simply human unpredictability. Let's now consider a concrete example where there are two robots with their initial positions and goal locations. The conventional space-time A* will pick a robot randomly, say robot 1, the red one, and then computes and reserve a path for robot 1. You can see this space-time diagram now with the time t as the vertical axis, how robot 1's path is planned as time progresses, from the initial to the next, and so on, while avoiding the static black areas as static obstacles. In this diagram, you have to imagine that the black areas are all through along the time vertical axis, which are not explicitly drawn in the figure. So the algorithm will register this planned path for robot 1 in the reservation table. Next, the algorithm plans robot 2's path while avoiding robot 1's already reserved space-time cells. Notice that if we only consider 2D, which is shown on the right, without the time dimension, then the path planning for robot 2 would not be possible because the register path basically blocks the blue robot from its initial position to its goal location. However, in space-time, robot 2's path planning is possible and shown as time progresses from the first to the next, and it finds a neighboring cell in the space-time to avoid the red trajectory. Here the key is that there are two cells in the 2D similarly shared by the two robots. Both the red one and the blue one uses the two cells in the middle of aisle, the second from the bottom, but actually in the time dimension they are separated by different times. Namely, the two robots will use these two cells, physical cells, spatial cells, in different times. So in space-time, there's no conflict there. So far, this is how the conventional space-time A* works. Now comes the critical difference in our robust approach. When we introduce a human worker, we don't just consider their exact planned path. Instead, we define two types of human behavior uncertainty. Temporal deviation RT, representing how much a human might be early or late compared to their planned schedule, and the spatial deviation RXY, representing how far a human might stray from their planned path. This means if a human is planned to be at position XY at time t, they might actually be anywhere within the spatial radius RXY and at any time between t minus RT and t plus RT. One example is shown on the right. If both RT and RXY are 1 and 1, then we will have to consider three different times, t, t minus 1, t plus 1, and in each time we have to consider the RXY, a bubble around the human. Here we only consider 4 cells around the precise location planned. Our robust space-time A* algorithm will consider all these possible space-time positions to ensure robot-human safety regardless of human deviations. Now let's return to the same example, but this time let's consider the red one is not a robot but a human worker. We illustrate how our proposed robust space-time A* algorithm. We illustrate how our proposed robust space-time A* algorithm works. We first plan the human worker's path from initial to goal and register this path in the reservation table. This is the same as before for a robot. Actually, exactly the same path. Next, which the difference comes. When planning the robot path, we must avoid not just the human's exact reserved positions, but all possible positions within their uncertainty parameters. And here again, we consider as an example, RT and RXY are both 1s. And then this expanded region around the human's planned trajectory in space-time will look like this. So these are all the cells in the space-time that have to be avoided when we plan the robot trajectory. This means that the path for the robot must be planned in a more conservative way to keep the robot out of all these possible human positions due to its possible temporal and spatial deviations. And in fact, we can find one in the space-time 3D, and maybe this can be seen more clearly in the figure shown on the right bottom corner here. The robot's path has to be planned around the black static obstacle in order to enforce the uncertainty parameters Rx and Rt, because visually you can see that the blue robot cannot use any cells inside the aisle between the two black static obstacle area without violating the uncertainty parameter requirement. The spatial separation must be 1 or above. So this example illustrates why our approach is called robust. It maintains safety guarantees even when humans don't follow exactly their planned trajectories. Here is our complete robust space-time A-star algorithm. The key innovation is in line 12, where we call the function expansion with uncertainty parameters RT and RXY. This function expands human positions around the planned path in space-time according to the uncertainty parameters to account for their behavioral uncertainties, thereby ensuring robust path planning for human-robot safety. The algorithm maintains the same overall structure as the conventional space-time A-star, but with critical enhancement for human-robot coordination. We handle dynamic task grouping and assignment, energy constraints, and human uncertainty modeling in an integrated framework. Our main results are threefold. First, our proposed algorithm provably solves the robust multi-agent pickup and delivery problem, ensuring all tasks are completed, energy constraints of the robot are never violated, all paths are safe, and most importantly, every robot-human path pair respects uncertainty parameters. Second, make-span performance is evaluated through case studies, which we will discuss shortly, showing the critical trade-off between robustness and efficiency. So there's no free lunch for robustness here. It tends to have a trade-off with efficiency, both for the make-span and actually for the computation as well, as we will see shortly. Third, the time complexity of the algorithm is shown here, where we can see that the uncertainty parameters Rx, Y, Rt directly impact computation cost. This should not be any surprise because the larger the parameters, the more collision avoidance needs to be taken into account, so more computation will be involved. Now let's present several case studies to evaluate our proposed algorithm. The first evaluation compares non-robust and robust approaches. In the non-robust case, namely with uncertainty parameters 0, 0, we achieve a make span of 291 steps with 30 robots. There's no human workers in this case. On the other hand, when the uncertainty parameters are set to be 1 and 1, 15 human workers and 15 robots, the make span increases to 330 steps. This 13% increase in make span is the price we pay for robustness guarantees. While this may seem significant, it's essential for safe human-robot collaboration in real warehouse environment, which the warehouse designer or manager should take into account. In the second case study, we evaluate how uncertainty parameters and human worker numbers affect computational cost. As uncertainty parameters increase from 1, 1 to 3, 3, make span grows significantly, both for 5 humans and 15 humans. Runtime also increases dramatically, reaching over 3,700 seconds, that's more than 10 minutes, for the most conservative setting. This demonstrates the fundamental trade-off between safety guarantees and the computational efficiency, which must be carefully balanced in practice. In the final case study, we examine a specific setting with uncertainty parameters 3, 3 and 15 human workers. Here we observe an interesting emergent behavior. The robots and the workers tend to form clusters, naturally segregating into different areas of the warehouse. We show these clusters by stopping this simulation and showing in this figure. This clustering behavior, in fact, in reflection, is a rational response to high uncertainty in the environment. When human behavior is highly unpredictable, the safest strategy is spatial separation. While this may well reduce overall efficiency, it maximizes safety in high uncertainty environments. This insight could inform warehouse layout design and human-robot coordination strategies in practice. Now let's wrap everything up. In this work, we considered a specific multi-agent pickup delivery problem with mixed human-robot environment. And specifically, we consider that the humans' behavior are uncertain. They can deviate in time and in space from their planned schedule and planned path. To deal with that, we have proposed a robust space-time A-star algorithm and evaluated its performance with case studies. And there are several immediate extensions to this algorithm that can be considered, including heterogeneous agents with different sizes, capacities, and speed. And there could also be dynamic clusters and also multi-layer, multi-floor facility in the warehouse. In addition, there are several further research questions we are looking at. One is adaptive robustness. Instead of fixed uncertainty parameter values, RT, RX, Y, can we learn these parameter values from data, from experience, and consider them as time-varying parameters throughout the course of the algorithm computation? Can we also incorporate predictive models for human workers' movements, behaviors? And finally, we would like to conduct real-world validation for the proposed algorithm to evaluate its performance and limitations in the real world. That's all for the presentation on this work. Thank you very much for your attention.